Okay, so in this video we've basically got the same control, sorry, not the same control diagram at all. This is first an open loop attempt on the buck converter, so that we should be able to control the duty cycle here and vary the output voltage in an open loop. With this slider here, we can vary the load on the buck converter. Here we've worked out the necessary coefficients based on the resistance values on the schematic of the buck converter design kit. This is the ADC gain, because we're using 3.3 volts and we're scaling that to 1 volt. The R5 in parallel with R7 is actually two 4K7 resistors. R6 is 1.2K resistor, which is giving these values here. Same with the input voltage scaling, and the current scaling is here. Okay, now this should give us the correct values. What we're doing in here is we've got a PWM, okay, and with the PWM we're doing it in at 100 kilohertz, as we've mentioned before. We're doing up down count, so we're switching off on the up count and switching on the down count. And one other important feature of this is we're sending out a start of conversion of for the ADC on the counter equals period. Okay, now there's a reason for this when we're doing closed loop control, and we can have a look at that. Okay, so here we're simulating the digital PWM, the actual peripheral inside the C2000 microcontroller. It's a type 1 peripheral. Okay, and we can even stop the simulation. So when we have the up down count here, this is our trigger. For example, for the start of conversion, we can trigger it on the period. If we switch on here, as we're doing, we're switching on the down count, we're switching off on the up count, and the inverse for the other PWM. In this way, we know that when we switch on, the start of conversion is separate from the switch on and the switch off. Okay, and the measurement of from the ADC should be in theory free of noise, free of the switching noise that occurs here, because there, regardless of the duty cycle. Even if we go up towards the period, obviously we're going to get a zero duty cycle there. Sorry, a maximum duty cycle, zero duty cycle when we go down, and in that way, here, if there's any switching noise, we don't see it when we do the conversion of the ADC for the output voltage regulation. Okay, so here also in this diagram we have another PWM controller, and what this controller is doing here is it's controlling the active load on the output of the buck converter. So we're switching that at 200 kilohertz in this case here. Okay, and it's just an up count on this one here. And in order to compile this, all we need to do is select it, go to Tools, Cogen. We're going to compile for the 28069, which we've set up here. 28069 is important, and 90 megahertz. Okay, so now we can go Tools, Cogen, and we can select the target interface blocks so that we can do a debug diagram. And we're also not going to select a flash because we want to run it in RAM and for easy debug. So we can compile this. Done, it's compiled. We can even view the C file. Okay, and this is done. Now what we will do is we'll move to the diagram here. Okay, this is done in a separate diagram in order that we run this diagram at certainly not at this rate, here at 100 Hertz. Okay, and we'll continuously running, so we'll continuously restart it. Okay, here, and whereas the difference with this one here is we had 100 kilohertz, which means that the the rate for the controller will be 100 kilohertz. For this diagram will run at the full 100 kilohertz rate on the MCU. So let's switch this on, connect to the converter. Now we're measuring already the input voltage here. We can switch on the converter. We've gone up to 3.25 volts, which we can see here because we're in open loop. We can just move this down around about 1 volts here, which we can see on the board. Move it back up. Okay, simply done. We've got the load on, so we've got 1.2 amps shown here because of this duty cycle. We can increase that load to 0.9. We've got 2 amps there. We can switch that off, switch it on. Obviously there's a base load there. Okay, what we're doing up here is we can trim the voltage. Okay, so obviously this is running fast. We can make these get slower. I wanted to check this, but we can move this up to the voltage that we desire, and we can check it on the hardware itself. We've got 3.31 volts here, so the trimming is good. Same with the input voltage. Okay, and we can use this trimming in a closed loop diagram, which we'll attempt to do next. So see you then.